Hello everyone, let's take a look at our next problem. Two people are playing a game which involves taking it in turns to eat chilies. There are 5 mild chilies and 1 hot chili. Assuming the game is over when the hot chili is eaten, and that I don't like hot chilies, is it a disadvantage to go first? What is the probability that I will eat the chili if I go first? How about if there are 6 mild and 2 hot? Interesting. So, I mean, my first thought is like you have to try and work backwards from a certain state of the game. There are other games like this where the first person to remove, or the person who removes the last piece on the board wins, and you kind of work backwards from there to figure out what the optimal strategy is and whether the first player has an advantage or not. Now that I think of it, though, this is actually not, there's no strategy here. There's no game exactly. It's simply two people taking turns eating chilies. I suppose this is just a version of Russian roulette, isn't it? So I'm going to imagine for a moment we have our 6 chilies, 5 mild and 1 hot. Okay, so now here's what I'm thinking is maybe we can write, it's actually a question of probability. And it's a question of probability, and we want to write down a recursive equation for the probability that you lose. Okay, so here's how I'm thinking about this. Let's forget about the fact that there are 6 chilies, 5 mild and 1 hot. And remember, the question is asked, it's sort of a two-part question. Is there a disadvantage to go first? And what is the probability that you eat the hot chili if you go first? What we're going to do is we're going to derive a relationship or an expression for the probability of you losing, given that there are a certain number of chilies left. Okay, so PK is going to represent the probability of eating the hot chili given there are K chilies remaining. Okay. And so, even values of K will correspond to one player, and odd values of K will correspond to the other player. P of 1 is, of course, equal to 1. If there's only 1 chili left and it's your turn, you're guaranteed to lose. Similarly, it's pretty easy to see that P2 is equal to a half. If there are 2 chilies left, we're assuming that the hot one is equally likely to be any of them. So if there are 2 chilies left, then the probability of you eating the hot one is a half. And if you do, you lose. If you don't, then you're guaranteed to win. Let's see if we can work out sort of just by common sense what P3 should be, and then maybe we'll derive a general formula in terms of K. So if there's 3 chilies left, my probability of eating the hot chili is a third, but then I have to include additional terms for if I don't eat the hot chili on this turn, and my opponent does not eat the hot chili on their turn. So the probability I do not eat the hot chili on my turn is 2/3, and the probability that they do not eat the hot chili on their subsequent turn is a half. So if there are 3 chilies left, the probability that I lose is going to be 2/3. Does this make sense? I suppose. Yeah, I guess because the probability should be higher than it's definitely less than 1. But does it make sense that it's higher than a half? I suppose because in some way I have to eat 2 chilies. Okay, let's keep going here for a minute, and we'll do these sanity checks as we go. Okay, P4, 4 chilies left. Well, the probability that I eat the hot chili immediately is 1/4. And the probability I don't is 3/4, and then we have to multiply by here. Well, we're trying to calculate the probability that I lose. The probability that I lose is 1 minus the probability that I win. But okay, so in the situation, if I don't eat the hot chili in this situation, it passes on to the other player, and the probability that they lose is P3. So the probability that I lose is 1 minus P3. Okay, so I'm starting to see the recursion that defines the sequence of P's. Let's compute what this number is, and then I'm going to do a sanity check and also maybe just sort of try and compute this in a different way and make sure I get the same number. It's a half. So if it's a half, I guess that does that make sense? You know what? I'm also starting to see another relationship here, and I'm going to guess what P5 is. P5 is going to be 3 out of 5. But let's make sure that we get the same thing when we use what seems to be this recursion relation, or the same reasoning that we did for the previous steps. And then I'm going to explain, if I'm correct, I'm going to explain how I got this. Well, why don't I just explain that first? We have 5 chilies remaining, and really, because we're alternating eating chilies, it's really no different than just distributing the chilies between the 2 players, but the player that goes first must get the additional chili if it's odd. Okay, so if there are 5 chilies left and I'm going first, I get 3 chilies, my opponent gets 2, and so the probability that I have the hot one is 3 out of 5, because I have 3 and there's 2 left over. But let's make sure, let's see if we get the same thing when we use this recursive argument. Okay, so P5 should be equal to 1 out of 5 if I eat the hot one immediately, plus 4 out of 5 times 1 minus P4 and 1 minus P4 is a half. So I do indeed get 3 out of 5. Okay, and so P6, by this reasoning that we just distribute the chilies between us evenly, should be a half. Let's again make sure, though, that we get the correct answer when we do it this way. So P6 is equal to 1 out of 6 plus 5 over 6 times 3 over 5, which is 1 over 6 plus 3 over 6. And I get a different answer now. Oh, no, I don't. I made a little arithmetic mistake here. 1 over 6 plus 5 over 6, 1 minus P5 is 2 out of 5. Yeah, so I do get a half. So this does work. Okay, so sanity check clears out. And you know what? We may as well just write down a general expression for pk, depending on whether pk is even or odd. So it's a half if k is even, and it will be equal to something divided by k. It'll be k over 2 plus a half, right? If k is odd. So I divide k by 2, I end up with, k is odd, so I end up with a fraction I have to round up. That's, in this case, the same as adding a half. And we can simplify this, get a slightly nicer expression. K plus 1 over 2 divided by k. So this is just divided by 2k. All right, let's substitute that here. K plus 1 over 2k. And let's just make sure that our answers so far, at least the odd ones, align with this formula. So P1, when k is 1, I get 2 over 2. When k is 3, I get 4 over 6, which is 2/3. When k is 5, I get 6 over 10, which is the same as 3 over 5. And, you know, given the reasoning, in fact, both of the reasonings, either the recursive way or just distributing it amongst the two players, I'm convinced that, you know, this is the correct answer. And so, you know, if you look at the pattern here for values of k, obviously it's always a half when k is even. When k is odd, it's always going to be greater than a half. And this makes sense intuitively if we use the reasoning that we're just dividing the chilies between the two players. If you're the odd player, or if there's an odd number of chilies and you have to go first, you have more chilies in front of you than your opponent. Now, as k gets extremely large, this probability will converge to a half. But the odd player is at a disadvantage if there are an odd number of chilies. Okay, so there's a follow-up question here, which is, how about if there are 6 mild chilies and 2 hot chilies? Now, for this one, it'll be a little bit more difficult to make the argument that we're just dividing the chilies between the two players before they even start eating. And the reason that's going to be difficult is because there's slightly more of a it's a more complicated combinatorics question, because, you know, one player could end up with one hot chili, or they could end up with 2 hot chilies. So what I think the recursive argument might be the way to go here, and then maybe we can find a nicer pattern between the P sub k's that we can solve for in closed form. Okay, so again, pk is the probability of losing with k chilies remaining. We're only going to consider k greater than or equal to 2, because if there's only 1 chili left, then someone has already eaten one of the hot chilies. Okay, so P2 is equal to 1 for the same reasoning that we had before. Now we'll see an immediate difference here. If there are 3 chilies left, you know 2 of them are hot, so your probability of losing is 2 out of 3. P4, well, I have the probability I eat one of the hot ones immediately, which is 2 out of 4. And then my probability of losing, if I don't eat the hot one immediately, well, that has a chance of 2 out of 4 happening if I eat one of the 2 mild chilies. And then conditioned on there being 3 chilies left, the probability that I lose is 1 minus the probability my opponent loses. Okay, so what do I have here? I have a half plus a half times a third, which is 2/3, right? A half plus a sixth is 2/3. Okay, and P5 is going to be 2 out of 5. That's if I eat one of the hot chilies immediately. I have 3 out of 5 chance of not eating a hot chili, and then I multiply by 1 minus P4. And what do I get here? 2 out of 5 plus 3 out of 5 times 1 minus P4 is 1/3. So I get 3/5. Okay. And PK is going to be, well, if there's K chilies left, the chance I lose immediately is 2 out of K. The chance that I continue is K minus 2 over K. And then I have to multiply by 1 minus PK minus 1. I don't know if there's going to be an easy way to solve this recursion formula. This is not really not exactly my strength, this kind of thing. I'm going to continue. This is certainly the right recursive formula. But I'm going to continue with a few more of these to see if I can spot a pattern. Okay, so I have a third plus 2/3 times 2 or 5. Oh, goodness. Oh, that's interesting. The probability stays the same going from 5 to 6, 3 to 5. Let me make sure I did this correctly. 2 out of 6 chance I lose instantly. 4 out of 6 I continue. If we continue, I do 1 minus P5, which is 2 out of 5. Okay. So this is a third. This is 2/3. 2/3 times 2/5 is 4/15. Multiply this by 5 over 5. Yep, okay, seems right. P7, this is what the question actually wanted. Wait, no, it's not. No, it wants P8. It wants P8. So we'll continue with this and see. Still, I'd like to see if we can spot a pattern. 2 out of 7 plus 5 out of 7 times 2 out of 5. Which is 2 out of 7 plus 2 out of 7, which is 4 out of 7. And P8, 2 out of 8 plus 6 out of 8 times 3 out of 7. Whoa, that's weird. Look at this. 2/3, 2/3. 3/5, 3/5, 4/7, 4/7. So if there are 8 chilies, it appears that there's no advantage to going first or second. You know, I'm seeing another pattern here, right? If we look at the numerators, 2, 3, 4, and the denominators 3, 5, 7. So, you know, based on this, my conjecture would be this would be my conjecture. Let's simplify these a little bit. This is k over 2, k minus 1. And this is k plus 1 divided by 2k. Where did I get this from? Well, I'm just matching the terms for 7 and 8, right? If k is even, the numerator is k divided by 2. And the denominator is k minus 1. If k is odd, well, what I'm going to do, I know that this number matches this number, so I'm going to add 1 to k and then use the same formula. So I've added 1 to k and then divided by 2. And here I've added 1 to k and then subtracted 1. How would we go about actually proving this? Well, you know what we could do? If I prove that this satisfies the recursion and that it satisfies the base case, then we're done, right? Okay, so k equals 2 is the base case. So when k equals 2, I have 2 divided by 2. So P2 gets a check mark. Now let's look at the recursion is going to be, I wrote it down before, 2 divided by k plus k minus 2 divided by k times 1 minus pk minus 1. Okay, so what we're going to do now, I'm going to break this down into two cases. I'm going to assume k is even, which means k minus 1 is odd, which means we use this formula. I'll substitute it in here and hope we get that. And then I'll assume k is odd and do the other case. Okay, so if k is even, then k minus 1 is odd. And what I need to do then is I need to substitute k minus 1 everywhere I see a k in here. All right, 1 minus k over 2k minus 1. What do I have here? K minus 2 divided by k. Here I have k minus 2 divided by 2, k minus 1. This is looking pretty ugly. Well, let's just keep going and see what happens. This first fraction I need to multiply by 2k minus 1 in both the numerator and denominator. Okay, I think we're going to get some cancellation. So I've got 4k minus 4 plus k squared minus 4k plus 4. Great. Divided by 2k, k minus 1. So everything in the numerator cancels except for the k squared, but one of the k's cancels in the denominator, so I end up with k divided by 2 times k minus 1. And is this the expression we had for even k? It is, right? So we ended up with this at the end of it, so we know, I mean, it seems like we solved the recursion there correctly. So let's go through and do this again, but we'll assume that k is odd. Okay, so then I have pk is equal to 2 divided by k plus k minus 2 over k times 1 minus. So if k is odd, k minus 1 is even. So I'm going to use this formula, but I'm going to substitute k minus 1 everywhere I see a k. So we're going to get some cancellation pretty quickly here. K minus 2 cancels with this k minus 2. So in the numerator, I have 2k minus 4 minus k plus 1. Divide by 2k. So this leaves me with k minus 3 divided by 2k. And pk ends up as k minus 1 divided by 2k. And is that what I had in my... Wait. No, got something strange going on here. I end up with k minus 1 instead of k plus 1. Let me go through this one again quickly in case I've made an arithmetic mistake. Don't want to bother having to just find it. So this is my recursive formula. K minus 1. Oh, I know what I did wrong. Wait, no, if k is even, yeah, no, this is correct. When k is even, this is the correct formula for pk. So pk minus 1 is equal to k minus 1 divided by 2 k minus 2. Okay, this seems to be correct. I've erased what I wrote before. I think I just made an arithmetic mistake in doing that, or a sign error or something. So, we wrote down the recursive relation. We evaluated it a few times. We proved that the pattern that we saw in the recursive relation holds. This is it holds by induction. I wasn't too explicit with the fact that we were doing induction here, but this is the correct answer when there's 2 hot chilies. When k represents the number of chilies left, and pk is the probability that you lose, or the probability that you're the first to eat a hot chili. And in terms of what the question originally asked, is there a disadvantage to go first? When the number of chilies is even, there's no disadvantage to going first or second. These probabilities work out the same. So that was a pretty cool problem. Thanks for watching.